We made it, guys. It's the last chapter, chapter 19, comparing counts. It's the chi-squared test, goodness of fit. That little letter there is called chi. It's spelled like this, chi-squared, but that's pronounced chi, not chi, okay? So I'm going to write out the equation for how to find chi-squared. It's the sum. It's ugly, so I just want to make sure you understand what happens here. Observed minus expected, all divided by, squared, all divided by expected. So this is a very different looking test statistic than we would normally compute. And notice that it's squared. So if you look at a picture of a chi-squared model, it's actually all positive. And let's see, actually, let's draw it like it were out of a test. We'd like graph our chi-squared, and then we'd shade always to the right. So these are actually always right-tailed tests. And the p-value will be the shaded region on the right side of our chi-squared value. So there are two kinds of chi-squared tests. We're just going to do quick notes on the goodness of fit test. And then I'm going to give the conditions, and I'll just remind you of the conditions when we see the next type of chi-squared test. So basically, the chi-squared goodness of fit, it's terrible English, but it actually helps me remember what this test is supposed to be. So this test compares an observed distribution. So an observed distribution of one categorical variable, so non-measurable, right? So it takes that and it compares an observed distribution of one categorical variable to an expected distribution of the same variable. So basically, we have an idea of how people might answer a question. That's our expected model. Okay, so we have an idea of how people might answer a question, which is how we expect it to happen. And we collect data to see if we were right. Okay, so this sounds a little weird, but we basically require two things. You're fine. What do we need to be given? Okay, I'm making too many videos in a row. He's getting anxious. What do we need to be given? A list of observed counts. Okay, so that's the first thing we need to be given. And the second thing we need to be given is a proposed model. So literally, how do we think the distribution is going to go? The first option is the same in all categories, right? This, way back in Unit 1, we referred to as uniform. And then the second option is that we are given distributions or expectations for each category. And we're expected to fill them in, and maybe instead of thinking everybody's going to fit and answer this question in the same, we actually think they're going to answer it in different distribution. So when I say categorical variable, I want to remind you that if I ask this question, I may answer it in words. So it's like, what is your favorite ice cream flavor? And then like, if I think it's uniform, I just think everybody's going to answer with the same probability. But what if I actually think that there's going to be more people who like some of the funky flavors and less people who like the more boring flavors? then I might give a different distribution of expectations for what I would expect in each category. So I'm literally either provided with enough information. So this has to be a lot of info. Okay, that's what this is for this particular. And for uniform, we don't get a lot, right? So not a lot of info is given if we're going to go with uniform, because that implies that we're really not told what's going on in each of the groups. We just think they're identical. Okay, I need a new slide. All right, here it goes. Hypotheses. This is really weird because for once our hypotheses are written out in words, but I'm going to give you fill in the blank sentences that we can literally always use. So remember that we think that it's the distribution matches or doesn't match a particular model. So we would say the distribution is consistent. Sorry, let's be specific. The distribution of, and then I'm just going to say blank. So like for my example from the previous slide, favorite ice cream flavor, right? So I'd say the distribution of favorite ice cream flavor is consistent with the model. Let's say the proposed model. So that means it does fit, right? Remember, this is called the goodness of fit. So the null actually says it is a good fit, and the alternative basically says it's not a good fit. The distribution of blank, favorite ice cream flavor, is, and then we just negate it, not consistent with the proposed model. And then, again, this is a chapter where it'll be really beneficial for you to watch the calculator videos in the previous learning materials. But for the most part, if we have a newer calculator, we would make a table like this. I usually write my outcomes, right, is usually like in words. Oops, I don't know what happened here. And then, so this would like describe the choices in the categorical variable, right? So if this were ice cream flavors, then I'd list all my ice cream flavors. And then I'd record my observed, if I can spell, my observed counts and my expected counts, okay? So I'd put all of these values into list 1 and all of these values into list 2. Then what you do is you run the chi-squared goodness of fit test on observed equals L1, expected equals L2, and our output, I missed something, guys. The degrees of freedom. Okay, so I'll help you. I'll put that in the bottom. Our output is chi-squared, which is your test statistic, and your p-value. Okay, one thing that we do have to include, are the degrees of freedom. So the degrees of freedom, remember, for the t-distribution are an estimate of the independent quantities after the parameters have been guessed. So in this case, we take the number of categories and we subtract 1. So the degrees of freedom, or DF in the calculator, we also need to enter the degrees of freedom here in the calculator. They are required to run this test, and then we go through and we can count them up. Like if I listed 7 ice cream flavors, then the degrees of freedom here would be 6. Okay, if you need help running this, there are steps in my notes, and there's calculator videos. I'm going to a new slide just to talk about what the conditions for this are, okay? So remember, right now we'd compare our our p-value to our alpha level and make a conclusion based on that. So we'd still make conclusions the same way that we always have, right? If the p-value is less than the alpha level, we reject the null. But if the p-value, oh, great, that's my neighbor's dog, is greater than the alpha level, we fail. Hopefully my 13-year-old dog can't hear well enough to hear that the dog is barking. So we fail to reject the null. Okay, now these are new, so let's discuss required conditions for this particular test. So this is a chi-squared test for goodness of fit. So the first condition is randomization, right? Was this a random sample? So random sampling used, that's what we're asking. And we really want to make sure we're checking if that has or has not been met. Okay, second condition we check. Counted data. This is kind of a silly one, but we have to check it, okay? Literally, are the observed data counts? Like, and what I mean by that, are they whole numbers? Whole numbers provided? If that's the case, then this condition has been met. They are actually whole number counts. So they can't be decimals or fractions or negative or whatever. Okay, and then finally, there's a sample size condition, which I prefer to call the expected, oh, here goes my 13-year-old dog. The expected cell frequency. I call it this because it's easier for me to remember what's happening when I call it this condition. So I want to check each expected count to make sure it's above 5. Or let's say that actually the rule is that it's at least 5. I don't know what happened here. That it's at least 5, right? So it could be 5 or more. So if we were going to be able to do a chi-squared test for goodness of fit, these 3 conditions would have to be satisfied.